And you see again over here link for GitHub repository. So copy this and clone it to a new folder. So say you have documents or something. Go to that and then git clone. Paste it with after the switch. I've already done it, so I'm not sure, but I'll wait for your confirmation. Also, if you just click on the link, you will be this page and there are better inscriptions. So it becomes updated after this hands-on session. And we'll be working because it's similar to do it in Python, and I'm hoping that everyone has Python. Create their systems, and if everyone has any one of you are already informed of that, that's also. So whichever thing, one of us use that or use reference from us. Forward. So those who have conduct, copy this part with conduct create -n. Change this virtual environment name to any name you want your environment to be. It's good to work with virtual environments so that it's not a bulky thing when you're working with the name, in your laptop and everything. It's also a neat way to develop things at one place. So say just write some name over here and give a Python version, something like 3.7 and number first. So we have given 3.1. So who do not have font down, do this Python -n virtual environment and give a name here. Don't copy it. But give a something into that. This. You see a temp folder that can close, and this includes a bin and include. And if you follow the instructions and then code, it happens. I will source the folder name, bin, and you see on the left there was this base search environment, which is changed to temp. You will have a similar, whatever name you give, that will come up. This is an important step. So, virtual environment changes so that. No, it can be announced. So if you want to come out of it after the final session, you just write contact deactivate it whether in the folder or even like deactivate the current general slide. Again, activities. Also, everyone has MPI software. Yes, yes, or not. When you get that, So even if everyone is not able to install it now, we can take some time and do that, but you can follow the background later. Yes. I'm studying.
So we are moving on.
These basic in the morning itself, that this message passing interface that's available in C, C++, Fortran, Python, and these open source implementations of MPI and OpenMPI that you're trying to install. This is language agnostic. So if you learn this in Python, you will also be able to do it in C, C++, and Fortran, and that's why we were choosing Python for this demonstration. And the basic idea is that there is a default communicator called MPI MPI underscore com underscore one. The communication between different processes, say 0, 1, 2, 3, 4, is going to be dealt with by this default thing, and you can have your own MPI communicators as well. So the simple send and receive operation, that is what we will try initially, is that you have something that is in processor 0, a data set, an array, or a dictionary, and you want to send it to one of them. So you do it as a com.send from the processor that has the data set, and you send it to one of the other processors, com.receive. Okay. So all the things that have been shared on in this Git repository will give you instructions on where are the good resources for MPI 4.5 and where are the basics for C, say. So when you have created your virtual environment, just update your pip install MPI 4.5 or use Conda for that, and go to the first file, say the hello world.p1. So the just a so if you invest into this folder, you will see that this boilerplate where is the basic structure that all of your codes are going to have. So you start by from MPI Popeye import capital MPI. MPI.com world will be realized as small com. This com.getRank gives you the rank of your processor. So you can think of that each of these code will be there as a image of the processors. So processor 0 will have a copy of code, processor 1 will have a copy of code, and so the others. So rank give you a number for that particular processor. And get size returns the total number of processors that are in this MPI communication. Okay, and when you do all these stuffs, and the final exiting the code, you have to MPI.finalize. For Python codes, you will not need to do this explicitly, but in C, you have to always initialize, and when you get out of the code, you also have to finalize. Okay, so we want to do some stuffs over here for communication, and I'm going to again say the hello world. So it's the same template. Now what we do is say
Supposed to type this?
You are also supposed to follow it. Those who can do it, please.
That one in.
First,
Yeah, that's good. Oh, I have to know. So these are equivalent of MPI center. In C. This is a block.
this is also I'm just telling well to if you want after this thing, what you should give in a sense about the so you have to follow this. You have to send the data, whatever thing you are sending, then destination, whom are you sending it to? And if you want to have a tag that it matches the tag that was sent and that was received, well, this is optional. But you have to send the data and the destination. So you have to write it in this way. Destination. Let's see. Actually, it is installed. Just take a quick off. This is. Just let's do this.
Yeah,
So one dictionary has been created by Rhymes. It doesn't exist in any other ranks. This will be sent to rank one, say, and rank one is going to receive it. If Everyone will train the data. Yes. So what you do is you do API run minus n number as a substitute. This is a Python file that you are executing. So Python. So speed. Rank 0 and 1 will you go. Data is defined. Yeah. So for L, that's correct. MPI is working for most of the time. So you had this template which was the MPI world communicator, the P rank, and the size. So now what you do, at first no one has the data. So data is defined as none. If P rank is 0, something, this is just dictionary. It can be an array or anything. How common is in the first argument, you put the data, which is, can I have the data where you want to send it? Destination is the tag to match when this thing was received with the other ranks. So this was just sent to P rank equal to 1. Then data which was received from source equal to 0, this is received in rank 1 here, and the tag if it matches, that will be saved in this data. And then you try to create it. So everyone please try to write it. We'll do some edits on this. How do we know to match what data and what receive is giving? That has to be done. So this I just wrote in world.py. The world.py is only this part written, and you will write this now. Okay. Yeah. So this receive is giving you this com.receive is giving you this. So you have to also store it in something. If you can't define anything, it doesn't know. It's like with MPI, it's a null pointer. That's why. Yeah. Then you can type
So on process,
you have to receive it somewhere.
so this is should find the
Yes. When you write MPI, you have to run it like
running.
we'll keep it like this for everyone.
So Python here, order it has to be.
So this is printed only when the receive function is in has been already done. So after it will create the data, then only rank 1 will be able to give this as not done, right? So now this is already there. So whatever 0 has, 1 will also have it. I'm just keeping this for everyone to write. So whoever has finished installing MPI profile, you see over here there is a file called boilerplate. Please copy it to whichever file you want to write. Don't say when you do this, you have to fill in whatever you want to do within this After comp and P rank has been calculated, before finalize, you can write your particle code. So let's write something here. So what we tried was very simple communication between person to spoken. So if P rank is not equal to 0, all of them will send a message.
Equal to this.
Yes, sure. Hello from percentage D, which is for an integer, and we write percentage P line. This is the complete message. Com dot send will send this message to the destination 0. Else, for all other processes, for PID in range, say 1 to P rank, write a message which is com dot receive or capital, both false in Python, but source was empty. Then range hide 0. Percentage D, the PID.
Yes. Which is very big, not different times.
The message.
This is the stop.
Let's try to this.
There's also an image that
So this now does this for all of the processes? Apart from 0, everyone sends this message to destination 0. 0 for all the ranks receives this message and prints it out.
Okay, can you just get the setup?
There's all the instructions are here in the GitHub repository results. You just write it here. I send on the link also. So whoever finds it easier to read this and do it, you can do it.
So this doesn't seem to work. You have to declare the write 5, 3, 4 to 5.
Whichever Python,
Let's do it.
yes. For this, there is so I'm so sorry. Here's a Python.
The code won't work because in the range it's 1 to P rank and the P rank is already set to 0. So it has to be the maximum number of processes that way. Yes.
So yes.
It should be
free. Thank you.
This. Run it.
I must Okay. So send receive operations, if you do one by one that you did over here, this is going to do one change by the processor, one communicated to processor 2, then again send this to processor 5, 6, 7, 8. It's going to take a lot of time. So rather than doing that, one can do a direct broadcast. So this can follow. It's like everyone simultaneously from processor 0. Every data that was there in processor 0 and not in others. You can also have a faster speed up by whichever the processor received it first is going to forward it to the processors, and this is done in the backend. You don't have to worry like how this communication works, but these are very important that broadcast, scatter, gather these are proper notifications that you will actually need when writing your MPI source. So we'll first try to do a broadcast. So let's the same thing. I copy m.py to this broadcast file. So let's first see what's there in this. The coming dictionary for only that field. Is everyone doing this at home?
Is everyone on the same page now? Yes. Or at least some. Every region.
So if P rank is 0, we'll create a dictionary. Again, name it say data. We'll add some methods.
Sorry.
You can actually also pass a list. So yes, just exists 0. Else you have to have a definition. Otherwise, you run into there.
So in this case, it's usually shares on the position for the last API we could have.
So then let's print what everyone has and let's see
Which is a discipline. As a
what cost, rank, percentage, D, whatever it has. We'll write percentage P rank and the data it has. And we also have to keep in mind that on the display, every processor has to display this. So you also write flash is equal to intro. And we'll check. Yes. So if you run MPI run minus in, only rank 0 has the data and others 0. I mean, none, no data. Okay. So let's first broadcast this dictionary to all other ranks. And this will be done by rank 0 because only that has the data. So let's do that. So data is form dot b cast, write it in small. That's working for data, which is 0. And then again print. So we just check and I'll be there on this. Okay. So you have line 0. You don't go and send this in stuff for this report, but you do a broadcast. On every processor, it will be called from the root 0 and the value. Single 0 is not done in the vacuum, but everyone has to call this longer big part. So it's like if we need a statement, you cannot put it in the number, so the words will not work. Yes. Roots.
Say no.
It's just for having everyone on the same footing. Otherwise, you do send, receive videos, gather those things.
I don't need to work. This side of the
So if you do the broadcast, this is what was the state before, right? See, everyone else, okay. Now try uncomment this. We do this pcast data from root 0. So root is the source wherever this data. I mean, these can also have the definition. This is just for us. These two see this. This was none and this now got filled. So you can try different things, but like in not bcast sends from root 0 will be saved in the data for all processors. This is the whole thing about broadcast. So if you just remove flush equal to true, all of these print statements will actually be executed after finalize. So you will not be able to understand when processor 0 finished it, 1 finished it, or second. Just whenever you want. Yes. It's done. You also rush into the screen here in that sense, in the terminal. So you see that statement. Otherwise, it will be done at the end. So next, you go to some integrator. So basic idea. So we understood what broadcast was. So one thing was broadcast. It was just one processor having something communicating it parallelly faster to all other processors. There are things like scatter. So you don't want to broadcast big chunks of data, but you want to spread smaller information to the other processor. So say if processor 0 has a big array, it can divide it to other processes and distribute the small bits to them. They do some work. And when they've done the process, that can be sent back to the processor 0 as a gather operation, where all of this is again combined from a bigger array, which can be more useful. Okay. Then there is a reduce operation. So say there are some numbers which have been calculated after some operation and it exists for all of the processors. Processor 0 can, you need to, in reduce, you do it only for one of the processors, which we are defining here as 0. So what it will do is it will say sum or find out the maximum, anything. So those operations can be done on the go while you are communicating those numbers. So in a reduce operation, all these digits can be summed up and that value be given to processor 0 by MPI dot sum as an argument. You can also try MPI dot max. So the maximum of whatever is in there can be there, minimum. Then there are a lot of bunch of things. There are the resources that have been shared in this Git repository. At the end of it, you can find pages where all of these are listed, and whatever your code needs, you can do that.
Process up to set back the data, whatever they calculated, and back to the 0 process.
One step.
From scanner.
So you also do operation on the yes, collects it and forms a bigger chunk of array that is organized in some order. It's just 0, 1, 2, 3 order. Here it is summing it up and one integer value for this example that it has.
It's like distributing a question paper. That's scatter. And when we last submit it, that's scatter.
Then your evaluator does reduce. Okay. So now you also might want that this final maximum of 2 is with all processors. Then you have it all reduced. So all of them have copies of their own calculation they had, but all of them also have this final result with them as well. So it's kind of the reduce followed by a broadcast of the final sum to all of them. Yes. So what reduce does is, given the operation and whatever data is in all the processes, it will combine them. If it's maximum, it will find out from all the results what's maximum. But this final value is residing in processor 0 only. If you want all of the processes to have this final sum, then utilize it and whatever they want, then that is called by all reduced. So you have this file also as a receive buffer in all of the processes. Okay, so we were two examples. So we will do a simple integration. That's the simplest thing that we can do. And balance. So trapezoidal rule is known to all of us. We can do it by one processor, but we want to sample it very finely, and we can do that we break this region and send it to different processors. They evaluate their own sum, they send it back to one of them or all of them, all reduce it, and then final integral is what you want to have as a result of your trapezoidal use code and implementation. So then this folder that was shared with you, there is a directory called integrate. We'll just go to integrate and see what files are there. So there is a trapezoidal.py file where the simple function is defined. This would work in serial, it would work in parallel as well. Right?
So what does it do? What does this function do?
So the trapezoidal rule is implemented over here. So you give a function, that's the first argument. Then you have the limits a to b, and n is the number of trapezoids that you break this domain into. The integral first has f of a plus f of b. And for all the remaining, for all the trapezoids, you break down this domain into, you add up for the function s. And integral times the step size b minus a by n is being multiplied at the end, and you return the integral. So this is just the trapezoidal rule.
Edges occur once, whereas the internal breaks occur twice because which
So this can be done as send receive, or it can also be done as reduce. Let's do the send receive one. Just look at the code. You don't need to run it, it's only. So the same thing, communicator defined as com, p rank as the process rank, size is the total number of processors involved, a to b is the limit of your integration 0 to 1. You have this many number of trapezoids to put the domain into, and this is the step size, basic part of the code. But now you want to do the local part. So local len is this. There's only one thing over here. That's for the simplicity. We are just having the number of ranks should be such that the n is divisible by it. So that's what is done over here. Local n is named n by size, or n to n level slash size. Local a runs from a times the p rank, local n times h. So a was the initial, your left edge. P rank 0 will have till local n, right? This will be 0. Local b will give you 0 plus local n times h. So this will be your local b. When p rank 1 comes over here, its local a will be a plus 1 times the local n. So it starts twice the that value. And then local b will have the next thing. This for every processor is determined which part of the domain they have to calculate. Okay.
Such things, it's very common to have off by one error. It will not, off by one error meaning you're missing one trapezoid. You're going from 0 to 9, but you wanted to go from 0 to 10. It's very common in such steps, so you should be watchful about that. Similarly, lin space can include the edge point, so you have to be aware of all these stuff.
So we will calculate the individual sums in integral, and a receive buffer will be kept just like data none was kept to receive things. So that pointer is already existing. for all the processes. So this is defined as numpy zeros 1. This has to be done because in Python you cannot send integers, you have to send arrays. So that's why this is a small part you have to change. I'll worry about here in C you can just send integers and everything. Okay, so I mean doubles and integral and the receiver. So this is the function that we'll try to evaluate, say 4 by 1 plus x squared. This 0 to 1 gives a value of pi. I know the answer. So integral for each of the local processor is calculated by calling the function traps. The function is passed, which is passed, defined over here. Then what was the order in the traps function? According to that, you give local A, local N. So this is calculated for each of the process. Each process has this integral 0 element calculated till this point. Now, if you want to communicate, this can be again done as a send and receive operation where p rank 0 has this integral, loops over everything, receives the buffer from all the other processes where this means this integral that was sent has been received over here. So some of this capital work I don't do. So this is a same point-to-point communication way of doing it. So the only thing that you guys have to do is now just replace this with a reduce operation that you just heard of.
So
You have the if rank is 0, the total was a variable in which this integral was saved, and it received a buffer from all the I processors ranging from 1 to the size of the processors. In the total, you add what you received, and what you received depends on com.send, which every other rank except 0 had sent to destination 0. This is a slower way to do it. A faster way is reuse operation. So in this folder, you have this file MPI integrate. Everything is written. I can run this also.
Every laptop has more than like less than regular 4 throws, right? In this room, so unless it's like 5 years old. Oh, but Swaraj is still from like one of them will see the first is who is the laptop?
This is the result from the send receive operation. You get the same thing. You just have one reduce. You have to write it. Right?
So general Python program we run this, there will be a certain time it will take.
Yeah.
So instead of waiting so for it dot time.
Yes. You just write time before this command. Before MPI run, write time. But otherwise, import time in your code, time of start and end of the that can be printed.
See the different dollars.
Yes, that also. Yeah, it will. But just change this MPI integrate reduce.py. This file is commented. You know what's happening over there. You just have to do a com.reduce operation. Right? You will find it's just one line. This part is working. As we saw by running the other file. Just change files one line. Com.reduce.
Perhaps you don't know the
Yeah, there is a link with it is already.
parameter list.
Yes, I can help with that. So you had this page in the comp astro HPC thing, you have the resources in MPI profile. You can just go look at the tutorial and search for reduce. See how it is run. Give it a try. Actually, do it. The operation you are doing is summing, so you use the same. The root is MPI.root. For you, it's line 0. MPI double is how the array elements are. So we also have that same thing. So find this one. Just about 6,000. It's hard. This is this. The data and the time are together in this format. This is the base diagram.
Passages.
Yes. So this part will vary and Python, but it's the basic thing. Please try it.
And what?
For really calculus for this. Not the second. That's also for me.
Can you run on like different number of processes?
So look at this.
What will not be used?
So how many points you have?
Okay, just there is a so try 2 and 4. See if the same. 2, 4, and 5. It's a super common.
1, 4, 6, 2, 0, 4, 8, 2, 2. Just sound like this.
Try 4. Oh yeah, it's different now.
Yes, yes.
It should not. Maybe there is some off by.
Something might say.
You should give identical answer to more than 13 significant digits because it's double precision, right? So there is a bug in this code which is a simple bug. Each process just makes you store. Fire.
Yeah.
Just play around with it. Their bargain is reduce. And the surface are to grow. If you think there is now that will last, what was I will